What's up, everyone? This is LeetCode 62 unique paths. This is going to be in C++. We've done this video in Python. I'm going to go a little bit faster, I think. Starting now, I'm going to start doing these videos a tiny bit faster in C++. Because I feel like it just gets tiring making a Python video and a C++ video for both of these, or two videos for each problem. I'll try and explain well my approaches, but yeah. But yeah, I might go a tiny bit faster. So you can read the problem statement if you want. I'm just going to summarize it. Basically, we're given a grid. We start at the top left and we have to get to the bottom right. We can only go down or we can go right from any particular cell. And we have to count the number of unique paths that there are to get from here to here, right? So I'm going to explain it with a picture. I think it's easier, right? So we have to go from here to here, and how many unique paths are there to go from here to here, knowing that we can only go down or to the right. So we can go like this. That's one path, right? This would be another path. This would be another path. This would be another path. This would be another path, right? So there's a bunch of different unique paths, and we have to count the total number of unique paths to get from here to here. We're always going to start at the top left, and we always got to end at the bottom right, okay? And so really the kind of approach or trick to understanding how to come up with a solution to this problem is understanding that for the first row and the first column, there's only one path to get to any of these cells, right? So first of all, there's only one way to get to our starting position because we start at it, right? So that's kind of like a base case. And these are also kind of like a base case because to get to this cell here, we can only take one path, right? Because again, we can only move down or to the right, so we'll never be able to go up. So there's only one path, right? So all of these cells here are actually one. There's only one path to get to any of these cells, okay? Same with the first column, right? The only way to get here, given this is our starting position, is to go like this. So there's only one path for any of these cells here. So that's kind of our base case. Now for the other cells, we take the sum of what's above. Sorry, I hit my microphone. We take the sum of what's above and to the left, right? And that should give us our total number of unique paths, right? And if you don't believe me, of course, you can draw it out, but I'll just give you a simple example, right? We can go like this, and we can go like this, two unique paths. For here, right, we can go like this, we can go like this, or we can go like this. So three unique paths, right? So for any cell, given that we set up our base cases, for any cell, the total number of unique paths is basically the sum of the cell above it and the sum to this with the sum of the cell to the left of it, right? So for here now, right, to fill these out, we take 2 plus 1, so it's 3, 3 plus 3 is 6, 6 plus 4 is 10, 10 plus 5, 15, 15 plus 6 should give us 21, 21 plus 7 is 20, that's a very bad 8. When I can't draw my 8s, sorry. There you go, 28. Now, this is example 1. We go to example 1, and guess what? Our output is 28, right? So there are 28 unique paths for this particular problem. So in terms of how we're going to approach this problem programmatically, well, first of all, we're just going to create a grid, right? We'll call it DP, and we'll initialize everything to 1. The reason we do that is it just kind of helps us set up our first row and our first column with 1s. And then we're basically going to iterate through the entire grid, but skipping the 0th index for the row and the column. So we're just going to handle the entire grid like this. We're going to handle all of this, right? And then at the end of the program, once we do our kind of looping through the grid and replace all the 1s with appropriate values for whatever's in here, we're going to take the last index for the row and the column, and it should give us our answer, right? Which would be this, okay? Meaning our answer is going to be stored right here. Okay, so I hope that made sense. I don't think it's too complicated, honestly. There are some DP problems that are really complex. I think this approach is actually pretty simple. It's just kind of setting it up and kind of coming up with a solution that is obviously a little difficult on your own, but I think understanding it is not too bad. So we're going to say vector int, right? We're going to say dpm, and we're going to say vector int We're just setting up a DP array, n by n, and setting everything to 1. Okay, pretty simple. Now, remember, we're going to skip the 0th index for the row in the column, so we're going to say int r equals 1, r is less than m plus plus. Okay, let's say for int c. For 1, we're also skipping the 0th index for the columns, remember. C less than n, c plus plus. And then in here is where we basically do the sum of the cell above it and the sum to the cell of the left of it. You can do either one, right? I mean, it is addition, so you can add the column first or the row first, doesn't really matter, but we'll just do column minus 1 first. Then we'll do row minus 1. If you're confused what I mean, I'm just saying that you can put this here and you can put this here. It's addition, so it doesn't matter. That's all I was saying. So yeah, we basically solved the problem already. I mean, it really is that simple. We just have to set it up first, and then we iterate through and count our unique paths for every cell. And then at the end, what we still have to do is return the actual answer, which is the number of unique paths to get to this particular cell, right? And so the way we do that is we just return dp of n minus 1, n minus 1, okay? I believe, unless I have a syntax error, that should be it. Yep. And yeah, that problem is really that simple. I hope this helped, and I'll see you guys in the next one. Peace out.